Welcome, ladies and gentlemen, to section 7.1, which is all about graphing exponential growth and decay. This is actually the first section in your Unit 7, which the unit itself is all about exponentials and logarithms. We first focus on exponentials, and then we get into logarithms, which is the inverse of exponents. So kind of like multiplication and division, our inverses, well, exponential and logs. Exponents and logs are inverses. But so we're going to first get into just like what the graph looks like and graphing these exponential growths and decays. And I'm going to say that I really do enjoy this unit because so many things in business deal with exponential growth, compound interest, for instance, those of you who want to invest, or definitely credit cards or credit in general is also an exponential growth that you're going to end up paying back. A good example of decay, of course, those of you who are driving probably realize very quickly that when a car is bought, it decays very, very quickly. And if you think the decay value or the depreciation of a car is bad, electronics is much, much worse. But we'll get into that, and that's kind of the fun part about this chapter. Hey, so section 7.1, I just want to mention, is a no calculator part. So while you can use your calculator as a reference as you learn the material, keep in mind that this would be on the summative in the no calculator part. What are we going to do in this section? Well, right here are the objectives. We're going to identify whether an exponential function models a growth or a decay. So I'm going to show you very quickly how you can tell that. And then you're going to actually graph them. So the first thing I'm going to say, just like we tend to do with all functions, including what we just got done doing, which was the sine and cosine or sinusoidal graphs, we like to talk about the general form. So here is the general form of an exponential graph, where A is the initial value, B is the growth or decay factor, and then X is the amount of time that passes, and Y is going to be your end result, or how much you have in your account or the worth of your vehicle or whatnot. So let me just write the A value down. It was the initial value, and it also, mathematically speaking, or graphing wise, it ends up being your y-intercept. So I think that's important to note. Intercept. Okay, so the initial value, so whether that's the principal value in an investment or the initial value you buy a vehicle or whatnot, that's the initial value. B is going to be your either growth or decay factor. And notice I'm not saying percent, I'm saying factor, and there's a huge difference between saying a percent decrease versus a growth or decay factor. So let me just write growth factor up here. And you know that it's a growth factor if the B value is greater than 1. And so if it's the B value is greater than 1, you have a growth factor or growth, and you would have a decay, and I'll say factor as well, if your B value is more than 0, so it can't be 0 because that doesn't make any sense, but it also has to be less than 1. And so if it's anywhere between 0 and 1, you have a decay factor. Anything greater than 1, you have a growth factor. And we'll get into a lot of that here as we move forward. Asymptotes, a line. We actually have dealt with asymptotes in the past, but I just want to make sure that you realize it's a line a graph approaches but never ever touches. So it gets infinitely close to the line, the asymptote, this hypothetical line I should say, but the graph never actually touches it. And the growth and decay graphs have asymptotes every single time. So again, we'll talk a lot about that. So I like this example 1 and 2 as far as a good example of what a growth function looks like and a decay function for an exponential. Just kind of throwing this out there, notice that here, actually I'm going to kind of take a step up here. It's the general form is y equals ab to the x, and notice we have an equation y equals 2 to the x. Notice where it looks like it's missing the a value. Well, you could always write this as 1 times 2 to the x. So I don't want you to think there's no a value. There is an a value, it's just not written. So the a value, the initial amount is 1, kind of like $1. and the b value is 2. And notice that 2 is, of course, greater than 1, so we're talking about a growth here, as defined above in that box, that anything over 1 is going to be growth. And so I'm going to input values in for x, and then we're going to substitute them, or actually input, I shouldn't say that. We're going to put in values in for x and get an output for y. So I'm going to just say that what makes it easier is if you just go -2, -1, 0, 1, and 2. Now, if you notice the graph, we have all the way the x-axis from -6 to 6, so you're not stuck with -2, -1, 0, 1, 2. If you really want to go -6, -4, 0, 5, 6, that's all fine. It's going to still give you the shape of the graph. I just tend to just do whatever's easiest, so I go -2 to 2. Anyway, so I'm going to put -2 into my x value to find my y, and this of course is back to the basics as far as you're putting -2 in for x. 2 to the -2 is the same thing as 1 over 2 squared, and that's going to give you 1/4. So you need to be at this point in the game in math comfortable with your negative exponent. So of course if you have a negative exponent, that means that you can bring it down to the denominator and actually expand it from there. Same goes then if you put -1 in for x. 2 to the -1 is the same thing as 1/2. If you put 0 in for x, again, this is something you need to know coming into the class. 2 to the 0 power, anything to the 0 power is going to give you 1. So even if you have a million to the 0 power, you're going to get 1. You put 1 in, you're going to get 2. Put 2 in, you get 4, because 2 squared is 4. Okay, so we kind of plugged and chugged a table here, and now we're going to graph it to get a general idea of what it looks like, this graph. We have, and I'm going to see if I can zoom in here. So we have -2 and 1/4, so that's like really, it's hard to graph in there, but do it the best you can. -1, 1/2 is up a little bit more. 0, 1, there's that y-intercept, which is also the initial value. Remember we talked about that the initial value is your y-intercept. And then 1, 2 is right here, and then 2, 4 is right here. So this is, and if you continued going negative on the x-axis, putting -3 and -4 and -5, and you would get smaller and smaller and smaller values, but you would never ever reach that value of 0. So I'm just letting you know that, ooh, and it looked like I can do better. You cannot touch that x-axis. And then as you can see, it's exponentially growing very quickly as it moves through that y-intercept. So this here is a great example of exponential growth with a growth factor of 2, which is really 200%, or you're growing at a rate, you're increasing 100% each time. And let's see, what else do I need to say? Oh, let's talk about this stuff down here. So the domain, stemming from first semester or Part A Advanced Alg, you know what domain and range is. Domain is where x makes sense, and in this case, if you look at it, it's going to be all real numbers. The range is going to be where y makes sense, and y is only defined at all values positive, or y is greater than 0. When you get to pre-calculus, we use domain and range all the time, but we use a little different. We use interval notation, which is a little complicates things for students. So just kind of make sure you understand domain and range is an important concept. It's extending from your previous courses, but that is something that just gets a little bit more meaty as you move through the courses. Y-intercept, we already said, is going to be 0, 1, and that again is affected by this initial value. And the asymptote, this is where we need to talk. The asymptote is right here. I'm going to dot it in, or dash, I should say, dash it in. It's really y equals 0. So you can't say it's the x-axis. You don't say the asymptote is the x-axis. You say that it is the equation y equals 0, because that is a horizontal line crossing the y-axis at 0. Okay, so those are important pieces of information that you need to be able to state once you graph your growth function. So now we're going to go do that decay and kind of show the difference here. So again, let's note that the a value is 1. It's out front, it's just not written, kind of like when we say x, we know it's 1x. And the b value is 1/2. And that value, 1/2, is between 0 and 1, so it is a decay factor, excuse me. And I'm going to use the same values. And again, this is not set in stone, but you do definitely need to graph 5 points. So I'm putting -2, -1, 0, 1, 2 in for x. So if I put, and I'm just going to do the first one for visual sake, but actually, you know what I'm going to do here is I'm going to erase that so I have a little more room. So we have y equals 1/2 raised to -2. Now, you should have been taught in Algebra 1 and also confirmed in geometry and first semester Advanced Alg that you can take the reciprocal and make it positive. So instead of 1/2 to -2, and you'd have to be able to do this without a calculator, you're going to have 2 or 2 over 1 raised to the second power. So again, when you have those negative exponents, they change positions from the numerator to the denominator, or vice versa. So this is going to be 4. When you put -1 in there into your equation, you're going to end up with 2. 0, 1. Notice again that y-intercept of 0, 1. And this is consistent. And again, remember, it doesn't matter what your growth or decay rate is. When you put a 0 in for that x value, it's going to go to 1. So unless your a value, you're multiplying the a value by something, or excuse me, the a value is anything but 1, you're going to have this intercept of 0, 1. So of course, if your a value is 4, you're going to take that 1 and multiply it by 4, so it end up being 0, 4. So the y-intercept changes with the a value. Put 1 in, you end up with 1/2, and then put 2 in, you end up with 1/4. Okay, so we're going to graph this, and again, I'm going to, nope, I'm not going to do that. I'm going to try, nope, I can't seem to make it go big. There we go. It makes it a little easier to graph it. So -2, we got 4 there, and again, if you really want, you could put -3, -4 in to get even a better look of a graph, so you don't have to just do 5 points. You could do even more than that. 0, 1, 1, 1/2, and then 2, 1/4. And so again, notice that this one, again, it goes through 0, 1, but it's decaying as it gets closer and closer to that x-axis. It's going to have that controlled asymptote. So that, again, there's that imaginary line, and a lot of times asymptotes are kind of like the mid-max line. You know, it's important to draw them in with a dash to kind of just as a reference. And this here, again, is going to be the equation y equals 0. This intercept right here is 0, 1. These are those important points that just are important to be able to label if asked to do so. Okay, so we have a domain, in this case, of all real numbers, just like the other example. The range, again, you notice is y is greater than 0. That's where it's defined or makes sense. The asymptote, again, is y equals 0, and the y-intercept is 0, 1. So kind of easy peasy once you kind of get going here. So if you look, this example 3 is very, very similar. Notice the b value. The b value is 3/2, so you're going to decide whether it's a growth or decay. So write that here, growth or decay. Pick which one, and then from there, graph it and state the domain, range, y-intercept, and asymptote. So it should look generally like the example 1 or example 2. It's going to be one of those. It's either going to look like a growth, where it grows over time, or it decays over time. So this is going to be something you do and show me that you're understanding it. And from there, we're going to go into a little bit more with the heavier duty shifting, graphing, translating, reflecting, all the good stuff that we did last unit with the cosine and sine. So you'll start seeing a lot of the patterns with graphing, and should anyway, from Part A, Advanced Alg, with parabolas and absolute value functions and all those kind of great things. Okay, so here's the general form of a translated, or like the all-time kind of exponential graph. The first thing I tend to do is graph the y equals ab to the x first, just like we did in example 1 and 2, and then translate or shift it using that h and k value. It makes it much, much easier as far as I'm concerned. So just to kind of rehash here, this is the initial amount. I'm going to abbreviate very heavily here, which just so happens to be the stretch. So just kind of, that's something to kind of keep an eye on. We also know it's the y-intercept. And then of course, now of course I should say it's the y-intercept before before you do any shifting around the axes. So just kind of keep that in mind. And then if it's negative, this is of course just like sine and cosine or parabolas, any of them. Negative is going to reflect across. Oh jeez, I'm having trouble writing. Across x-axis. And B, again, is that growth or decay factor. And as that changes, the only thing that's going to change is how fast it grows or decays. So it's going to change what the graph looks like if that growth factor is more or less. But you still have that general look of the graph. It never changes. If it's a growth, it'll look like a growth. If it's a decay, it looks like a decay. The H, of course, just like in the past, is the horizontal. And we called it a phase shift last unit, but it's the horizontal shift, which of course is left to right. I'm not going to write that. You guys can write that if you need to. So it's that left and right shift. And then the vertical shift is the K value. And again, that's an up and down shift. And at this point, you should pick up on that pretty quickly. Okay, so let's talk about this. So I have an example 4 and 5. And 1, looking at it very quickly, I can tell this is a growth. How do I know? Well, my B value is 4. And here we have a decay. And how do we know? Because the B value is 1/3. And again, what I tend to do is I first graph almost like the parent, if you want to think of it that way. So I'm going to first graph y equals -3 times 4 to the x. And I'm not going to graph it in the sense of like a solid graph because that's obviously not my final product. So I'm going to do that dashed. And because I know anything dashed is noteworthy, but it's not the final product. And again, we use dash for asymptotes and again the mid and min and max lines for sine and cosine graphs. So dashed, we all know what it means. It's just kind of there, but it's more for reference. Okay, so this is the one where I'm going to use the table. So this graph is how I'm going to use the table. So I'm going to put -2 in here, -1, 0, 1, and 2. And again, those are not set in stone. It just makes life a little easier. Just because of who I am, I'm going to put 0 in first because that's easiest. So when I put 0 in for x, 4 to the 0 is 1. 1 times -3 is -3. So that's the mathematical approach to it. But of course, we know that that A value is your y-intercept before your horizontal and vertical shift. Now if I put -1 in, and again you can do them in any order, and you can even pause this and do it on your own, but you do again need to be able to do it long-handed. So actually I'll do -2 first. So if I put -2 in for x, I have 1/16. Again, that negative exponent shifts it down to the denominator, and then you square it. So 1/16 times -3 is going to give me -3/16. If I put -1 in, I end up with 1/4. 1/4 times -3, and that's where I get -3/4. And I don't have a lot of room here. The number 1, I'm sorry, 1. If I put 1 in, I get 4. 4 to the first is 4. Times -3 gives me -12. I'm totally off my graph already. 2 goes in, I end up with -48. So that's like way out there. So I'm going to not draw on my graph. I'm going to try making it big here again to make it a little easier to graph. And again, I'm doing this in dashed lines. It makes it much easier. So -2, -3/16. I mean, we're talking about like right there, you know. -1 and -3/4 is going to be about, I don't know, about right there. 0, -3, we're all good there. 1, -12 is off the graph. So I'm going to do this in a dashed line. A lot of times I by accident say dotted. And notice how fast this is decaying. It's like super, super fast. And again, we have this asymptote that we can't be touching. Okay, so now I'm going to switch colors here. I don't know what color I'm going to go blue. Now I'm going to do my horizontal and vertical shift. Looking at it, I know that I am going +2 on the x-axis, and I just covered it. Positive 2 on the x-axis, so I'm going this way 2 units, and then I'm going to go up 1 unit. And all that is coming from this right here. So we know that 2 is your h value, your k value is 1, and you shift it from there. Okay, so notice, I do want to say this, I almost kind of forgot to mention it, is that notice that while this is a growth, or it should have been a growth, it's actually reflected across the x-axis, so it looks a little funky, right? So I just want you to realize that, and I'm going to draw this, without the reflection of that negative in front of the 3, in front of that a value, it would have looked like this, right? Oops, that's a typical growth curve. Of course, it would have gone through 0, 3. But because of that negative, it reflected right across this x-axis, so that's why it looks the way it does. Now I'm going to get rid of that because I just wanted to talk about it. And I'm going to take some big points, obviously. The big one is always this intercept right here, that 0, -3, and do that shift with it. So I know I'm going right 2 and up 1. So this here is that new point. Now you can do that same thing with each one of your points. Now it gets a little bit dicey because of the way they look, but you're going to go over 2, up 1. So we're right at about there. Notice that the x-axis, or y = 0, is not our asymptote here. And that is something I think I'm going to stop and talk about. So if your asymptote typically was this right here, it was usually the x-axis, the thing that's changing that y, or that asymptote, is going to be your vertical shift. Just like the midline changed with sine and cosine, well, that k value causes that vertical shift, which also shifts the asymptote. So I'm going to get rid of my original asymptote here because I don't want it there. But I need to remember that my asymptote has shifted from the original up 1 because of this k value right here. Okay, so I know my asymptote is y = 1. And so that also kind of helps you graph in your data because you know that it's going to look something a little like this right here. Oh gosh, I probably could have done a little bit better, but I think you get the idea here. It's this curve right here. I'm kind of not doing very well. Okay, so that is your graph. Now let's answer some of these questions down here. It says, what is the domain? Well, you know what? It's all real numbers because you're going from negative and positive infinity on the x-axis. There's no constraints on you. We know what the asymptote is. I'll put that right here, y = 1, so it's kind of nice. Again, that's affected by the k value. And then we know the range. Now it's usually y is greater than 0, but because we reflected and we shifted the whole thing up, you know that it's going to end up being y is less than 1. And notice how these two always work together. I don't know if you picked up on that. If you look at the other two examples, they always work together. So just kind of keep that pattern in mind. That kind of helps as well. Okay, the y-intercept. Let's talk about the y-intercept. It was 0, -3, right? So that's where the y-intercept is. But if you look, the new y-intercept is going to be right, oh boy, it's right, I'm going to switch colors so you can see it. It's right here. Now you have to calculate that point. And if you start thinking about that, I don't know if you really looked at what happened here, but that -2 point, when you shifted that over and up, you ended up with a new y-intercept. And you know, there's a couple ways to do this. Long-handed, you know, at this point what I tend to do is say guesstimate it. I can show you how to get a really accurate graph or excuse me, that y-intercept, so that you can calculate it long-handed. But really, when you get to pre-calculus, you end up guesstimating it. And the other thing is you use your graphing calculator to find the y-intercept, which we're going to show in the next section. So anyway, I'm going to just say that the y-intercept here is, I'm going to keep it in red here, is 0 and 13/16. Okay. And just to show you the mathematical way of doing it, just because I can, I'm going to go -3/16. Look at where you're starting there, and you're shifting that over 1 over. So if you do that, or excuse me, 1 up, and if you do that from there, you're going to end up getting a common denominator, which is 16/16, and that gives you 13/16. So that's where this value is coming from right there. So my graph is a little hard to see. Hopefully with your pencil you can get a little bit more accurate picture of where that's falling, and I just wanted to make sure that you saw the math involved, or the calculation involved with coming up with the exact value. Okay, so let's do this one over here. Again, we have an a value of 2. I don't want to do it in red. I don't know why. Red feels so formal. A is equal to 2. The b value is 1/3, which means that we have a decay like we set up here. So I said it already, so I'm going to not rewrite it. But that's that right there. The h value is -1, so we're actually going left 1. Don't forget, it's always that opposite of what you think. It's x plus 1, but it is shifting the opposite. It's not going positive 1, it's actually going -1. The k value is exactly what it looks like, which is -4, so that means you're going down 4 units. And again, when you graph it, just first, I ran out of space up there, I'm going to first graph y equals 2 times 1/3 raised to the x. So I'm just not incorporating the shifts of the h and k value. I am just graphing what you could almost think of as the initial, the parent. So anyway, this is -2, -1, 0, 1, 2, and again, if you want to shake it up, do so. If you put -2 in to that, remember you're dealing with a reciprocal, so you end up with 3 squared, which is 9 times 2, that gives me 18. So you need to be very good mentally with those exponents. And that's why in that part A, you had to work with that a lot without a calculator. Okay, so anyway, if you put -1 into this graph, equation, you end up with 1/3 raised to the -1, which is the same thing as 3, or 3/1, times 2, and that gives me 6. Put 0 in, we get 2, that initial value of that a value, 2/3, and then 2/9. And again, these are not that beautiful to graph, I get that, but let's just kind of get them in there. So I'm going to make this kind of big here for me again. And so -218 is off my charts, but I have -1/6, then I have 0.2, then I have 1 2/3, which is about right there, and I have 2, and I know it's going to get a little closer kind of thing. And I want to do that dashed because this is not my final product, is it? And maybe you don't even want to draw this. That's fine. You can shift the points right away if you want. So what I guess I'm saying is you don't even have to graph this. You can just kind of visualize where these points are. And I'm putting them here just so that I can show you what I'm talking about. And I know that each one of those points is going to be shifted over 1 and down 4. 1, 2, 3, 4. So there's that one. Over 1, 1, 2, 3, 4. There's that one. And then this one's a little tricky. Over 1, 1, 2, 3, 4. And there's my y-intercept. So kind of keep that in mind, that fella is the one that we're going to look at for the y-intercept. Over 1, 1, 2, 3, 4. And it's not perfect, but it's pretty good. And then again, I know our original asymptote is right here, so I'm shifting that down with the k value. So 1, 2, 3, 4. So here's my actual asymptote. And again, I'm going to first get rid of that other one because I don't want you to get confused which one is the real one. Okay, so I'm going to put this. Noise effects help, right? Okay, so there's my asymptote at y equals -4, and my amazing graph. I just said red feels too formal, but I'm doing it anyway. And there it is. And again, we need to kind of look at what that intercept is. That's kind of an important spot. So we'll kind of talk about that here in a minute after I shrink it a little bit. Okay, so the domain, of course, as you probably figured out, is all real numbers. The range, this is kind of interesting because you're looking at the y. Where does y make sense? And really that asymptote, which we know is y equals -4. So then we can just say, hey, it's all the values greater than that. And the y-intercept, again, this is a little tricky, and you need to be able to do it. So let's just kind of look at it a little closer. Again, that last point, or no, not that last point. This is the one that ended up when you shifted over 1 and down 4. That's the one that ended up ending on your y-intercept. So I'm going to, let's see, what's that point? We ended up starting at, that was 2/3, right? I'm going to do the work down here. So 2/3. So I'm looking at this point right here. So that y-coordinate is 2/3, and I'm going to subtract 4 from it. Why? Because that's how many we went down. Kind of like the other one, we added or added the 1 up, so that's why we added 1, or 16/16. Well, here's the thing. We got to be able to do fractions here, so I'm going to get a common denominator. I have, this is 3, this is 12, and we end up with -10/3. And I kind of alluded that you didn't have to do this in that first example. That is not the case. I mean, I guess what I'm saying is I teach pre-calculus a lot, and eventually we just use a graphing calculator. But in Advanced Alg Part 2 or B, you do need to be able to shift that graph and notice which point is actually shifting onto the y-axis, and make sure that you use that k value to actually calculate the y-intercept. Kind of like thinking to myself that I may have given the wrong impression there. Okay, so that is it, really. That's how you graph exponentials, whether it's a decay or a growth. Now, you're not applying it yet. That's the next section, but hopefully you got a pretty good handle on just being able to graph. Okay, so now get some practice down and see how you do it. Take care.